Okay, well, welcome back if you're still with me. I appreciate that, and I think today will be pretty enjoyable and pretty edifying to those of you who are interested in understanding electronics, particularly tube gear, but just electronics and electrical engineering in general. Because today we're going to be getting into the principles of Ohm's law, as well as understanding power transformers and turns ratios. And we're going to be applying that a little bit to the diode and wrapping up and finishing our discussion of the diode. Next time we're going to begin with the triode. And we're still all on the theory part. We haven't started discussing how to plot load lines and design vacuum tube amplifiers. I decided not to dive right into that because that's what everyone else does. And I wanted to give you a really firm understanding of how these things work. I think that's important. Particularly for those of you who really appreciate and like vacuum tube gear. Knowing how they work, knowing how these beautiful little devices function it actually makes things more enjoyable. Owning the equipment, I believe. Does for me at least, so I hope it does for you as well. That's why I put the effort into this. Okay, I hope that today's video will be no more than a half an hour. I try for a half an hour, but I end up going over. All right. We're going to begin with just basic Ohm's law before we get into the resistance of a diode. And again, I've told you all this stuff we're doing now is developing a foundation for the understanding of a triode. And from there, everything flows. Because a triode is nothing more than a diode with a grid in it. All right. So let's talk basically about Ohm's law. And what we're going to be talking about today are three scenarios of Ohm's law: an open circuit, a short circuit, and a circuit with a resistor in it. There are different variations of Ohm's law. This is Ohm's law right here, by the way, but you could solve for any one of these variables if you have the other two. If I have resistance and current, I can find voltage. If I have current and voltage, I can find resistance. That's what we're going to be doing today. Right? If I have resistance and current, I can find voltage. So you could just switch this equation around. We're not going to do that today because we're interested in resistance today. So resistance of a component in question is equal to the voltage dropped by the component divided by the current that runs through the component. And I want to exemplify that with three different scenarios. So the first scenario over here, I've got a basic circuit, and this is we'll just call this a battery, or you can call it a power source, and we're dealing with direct current now. You can picture this as like, just a battery. And here's our positive terminal, and there's our negative terminal, and we're going to use conventional flow. Conventional flow is typically used in circuit analysis, and conventional flow means we assume that electrons flow from positive to negative. There's a historical reason we use this. All right. So let's say that I know I have a 20 volt battery and I've tested it. I've put a voltmeter across it and it's 20 volts. Let's say somewhere I have a little ammeter in here, a little meter, and I'm reading that I have 0.04 amps or 40 milliamps flowing through the circuit. But I don't know. Now here's a load right here. This is a load. It could be anything. It could be a resistor. It could be a lamp. It could be a diode. It could be a vacuum tube diode. It could be anything that resists the flow of electrons or current. Resist the flow of current. But I don't know what that resistance is. And as you can see, it's fairly simple to calculate. So the resistance here, now we know there's no other elements in this circuit to drop voltage. So all of this voltage right here, this 20 volts, is going to appear at the top of the resistor. And at the bottom of the resistor, all we have is wires. We're going to assume they're perfect wires. There's no voltage dropped across those wires. So we're going to have 0 volts down here. So we know there's going to be 20 volts dropped across that load. So resistance is going to be our 20 volts right here divided by the current flowing through it, 40 milliamps. And that's going to yield a resistance of 500 ohms. Now I'm going to get back to that value in a minute because it actually is pretty reflective of a resistance of a vacuum tube diode at a certain point on the plate characteristic curve. DC, direct current. So all this means is that we have this resistive element that's resisting the flow of electrons to the point where only this current will flow for this amount of voltage. If I increase the voltage, let me put it this way. If I increase the voltage, what do you think is going to happen to the current? Well, more current's going to flow because I've increased the force. Okay, what if I keep the voltage constant but decrease the resistance? Same thing. Okay, that would be like keeping this constant and reducing this. Well, that's going to result in I'm not going to do that in Ohm's law. Well, current. Let's rearrange Ohm's law. Current is going to be voltage divided by resistance. All right? That's just rearranging Ohm's law. Now, so if I decrease the resistance, like I just said, I wasn't going to I'm already on a tangent. If I decrease the resistance, this number gets smaller. That means this number gets larger. That means the current goes up. All right? Now that's just an aside. Let's get on to two other scenarios, the short circuit and the open circuit. Not that they're necessary to get into, but it's really helpful to envision this. And it will be helpful in the future. All right. Stare at this for a minute. What do you think has happened here? I've removed the resistor and I haven't replaced it with anything. It's an open circuit. In fact, we call it an open circuit because there's no path for electrons to flow. So we really don't even have a circuit. Circuit means circular. It's a path. We don't really even have a path. So, in essence, if we don't have a path for current to flow, we're not going to have current. I is going to equal to 0. Okay, I will be equal to 0. No current can flow. That's like the equivalent of having a switch and having that switch open. Like the switch on your light bulbs. Your lights around the house. The switch is open. The lights aren't going to light. Okay, that's an open circuit. If the switch was closed, the light to a light, that's called a short circuit. All right. Let's get back to this. Let me erase some of this stuff. Okay. Get back to my pen. All right. So, as I mentioned, open circuit, no current can flow. So what is the resistance of this load? Well, it's really undefined. Because when you think about resistance, it's voltage divided by current. So that would be 20 volts divided by 0, and any division by 0 is completely undefined. Undefined. Now you could think of it. It's helpful to think of it even though it's not correct. It would be helpful to think of what happens as you take this current, given a number, let's say we started with 40 milliamps below, and lower it and lower it and lower the current, and keep lowering it to the point where we approach 0, but we haven't reached it. Well, the resistance will approach infinity. We'll never get there because you can't, divide by 0, but it'll approach infinity. So you can, it was often helpful when I was in college to think of an open circuit as an infinite resistance. However, in reality, it's not. And I'll tell you why. And I'm on a tangent now, but this is useful to know. This is completely an aside. Right now, current's not going to flow, but what happens if I increase this voltage to some hellacious number, like, 30,000 volts? At some point between this terminal and that terminal, depending on how close they are, you're going to get arcing or a spark. You're going to get ionization of the air. Basically a mini lightning bolt. So there's always some path for current to flow. And that's why I'm reluctant to say the resistance is infinite. Because there's always going to be some path for current to flow if the voltage is high enough. Pretty cool, huh? But in general, an open circuit means no current will flow. We're going to get back to when we look at the diode plate characteristics, what that really means. Let's look at the other scenario. In this scenario, I've replaced the resistor with a wire. And we're going to assume these wires are perfect wires, 0 resistance, effectively. What will happen when I apply 20 volts? Or any voltage for that matter. Well, this is called a short circuit. And the circuit is shorted. And there really is no one definition of what, how much current's going to flow, because let's look at our equation. Resistance is equal to voltage divided by current. And with a short circuit, there is no limiting factor as to how much current can flow here. Theoretically. So you could think of this as, very briefly, an infinite amount of current will flow, even though that's not practical. But it's a short circuit. So very briefly, this current here is going to spike really high as it approaches infinity. But something's going to happen practically. These wires in reality do have a resistance. This battery also has a limit to what it can produce as well, but I won't get into that. But let's look at this scenario. These wires in reality do have some small amount of resistance. And as this current approaches infinity, right here, well, power, one equation for power dissipation is I current squared times resistance. So even though this resistance of this wire is very small, let's say 0.0001 ohms, this current is going to go so high, and in the equation here for power it's squared, so it's going to run exponentially high, and at some point this wire is going to dissipate so much power it's going to burn up. Something's going to burn up. It's going to heat up and open. It just won't be able to handle it. So the point here is, while effectively the resistance of a short circuit right here is 0. We call it 0. Let's see if I screwed that up. Yeah, the resistance is 0. I didn't screw that up. I just wanted to make sure I'm consistent here. So while effectively the resistance is 0, and back here we said effectively the resistance is infinity, I just wanted to clarify this, make sure I'm consistent. And we could look at this equation, and we can say just for a brief period of time, R is equal to voltage times current. And for this brief period of time, we have 20 volts divided by something that's going to be approaching infinity. Okay, so if this approaches infinity, the resistance will approach 0. But again, it's not practical because something's going to burn up before we reach 0 and before current reaches infinity. Okay. Hope I didn't confuse you there. Everything I said is true, but okay, but I just wanted to clarify the difference. Okay? We need a resistance. We always need a load. We need something to limit the current. Again, open circuits, nothing will flow. Short circuits, we have too much current. So we always need something to limit the flow, and that's the point here of current. And that's what we have, a load of some kind. There are AC loads and DC loads, but in this case it's a DC load. And the load, the resistance, serves to limit the flow of current per whatever voltage we're applying. All right, good. Now, let's apply this back to, and this is a chart that I kind of concluded with last time. This is our diode. There's the diode. Let me redraw it again. Here's the cathode, and there's the plate. And we are going to apply a positive voltage, and this is a variable voltage source. We're going to go from 0 and ratchet it up to roughly, say, 350 volts. And we're going to have a little ammeter right here. And as we increase the voltage in our diode on our plate from 0 to 350, we're going to read the amount of current that flows. So cause and effect. Down here, the plate voltage is the cause, increasing the plate voltage. The effect will be something happening to the plate current. In this case, an increase. And here's where I'm going to apply what we just talked about, Ohm's law. So when we're down at 0 volts, effectively, even though I mentioned before there's a very tiny amount of electron flow, it's insignificant. and we ignore it. So effectively at 0 volts right here on plate voltage, we have 0 current. Now as we start increasing the plate voltage, here's 50, we hit a point where we start increasing the current that's flowing through there. In this case we have about 9, let's call these milliamps. All right. You can see as we continue to increase, let's go to 200 right here. 200 volts on the plate. We've increased our plate current to something on the order of 49 milliamps. So that's the effect. Now, let's figure out what kind of resistance. Now, if our diode did not resist, let's say it is an open circuit. Where'd my cursor go? There it is. Let's say for a minute it's an open circuit. And so let's replace, well, let's just pretend for a minute this is an open circuit. Open circuit. And we start increasing the plate voltage. As we mentioned before, no current can flow. So if there was such a line here we could draw, it would be right here along the x-axis. It would look like that. So every step increase in our plate voltage, we still have 0 current. Let's look at the other way around. Let's pretend our diode is a short circuit. A short circuit. That would mean for any given voltage, and I'll just pick one voltage, but you can pick any one you want to. For any given voltage, let me just pick 100 volts. I mentioned to you before that in a short circuit, there is absolutely no resistance to flow. So our current, and it's not really on this line, our current is just going to head for the hills. It's going to head for infinity, but at some point something's going to blow up like that. But as you can see, we have neither one of these situations. What we have is this line right here, this linear, and it's got a slope to it. What that means is our diode is acting like a resistor. It's got some resistance to it. It's neither an open nor a short circuit. And these resistance characteristics play an important role not only in diodes, but also in triodes. So let's look at this. We're going to start with the DC plate resistance of the diode. Direct current. Okay, direct current would be like, again, having a battery, plus and minus. When we talk about AC, the symbol we sometimes use for an AC source looks like that. Meaning the current, okay, here's how the current would flow, just constant like that in DC, direct current. In an alternating flow, we kind of have to look at time. Right here, time versus voltage. And at time 0, let's say the voltage is at 0, then at a certain time it rises, then it falls, then it rises, then it falls over time to some positive value, back to 0, then to some negative value, and the cycle repeats. It's called a sine wave. All right, we are looking at DC right now. We're applying DC. So back to resistance. So how do we know how much this thing is resisting? We know that our cathode, not cathode, we know that our rectifier tube, our diode, I should say diode, is acting like a resistor. It's neither an open circuit nor a short circuit. So what resistor would it be acting like? What value? So let's go back and apply a voltage, and let's pick. Okay, this goes back to this example right here, 20 volts. So let's pick 20 volts. That's why these curves here, these characteristic curves for vacuum tube devices, become important for designers. So let's pick 20 volts and find out what this is right here, this resistance. So we pick 20 volts and we go up on the cause, the x-axis. 20 volts is the cause of the current flow, and we intersect the characteristic line right here, and we come over to the effect axis, the y-axis, and we see that we get a flow of current through the diode of 40 milliamps, 0.04 milliamps. Okay? Now, let's go back to this first example. Let me erase something. That's exactly what this first example was. Right here. Alright? So we can calculate the resistance to be R equals 20 divided by 0.04, and we get 500 ohms. So that diode is acting like a 500 ohm resistor at that point. Now on this plate characteristic curve, we've plotted these two other places. You can see it's pretty linear up here, but the slope kind of decreases down here. So here we've plotted 8 volts on the plate. We've gotten 10 milliamps out, and you can run the numbers, okay? R equals voltage, resistance equals voltage divided by current. Let's go back. I won't bore you with that now. And we'll get a resistance, we call it the plate resistance, of 800 ohms. We can do it again up here for 28 volts. And at 28 volts we get something like 65 milliamps, something on that order. I don't know what it is, it's close to that. And run Ohm's law, and we get a plate resistance of 422. So generally in most of this linear area here, first of all I want you to note that as the plate voltage increases, the resistance of the diode decreases. That's typical characteristic of an unloaded. There's no load here. We're not loading the diode down with a load. That's typical characteristic of an unloaded diode. And plate voltage increases, its resistance decreases. It's kind of intuitive if you think about it. Or more force on the plate attracting those electrons. And vice versa, plate voltage decreases, resistance increases. Starts really going up down here when this slope starts to decrease. Now this is DC, and we can do the same thing with AC. And I'm not going to get into detail here, but there's an important thing to note. There's our cathode, there's our plate. Here we're going to use alternating current, and here's our ammeter right here. Now with AC, with DC, we just pick a voltage. But with AC, our voltage is swinging between two values. So it's not static, it's not sitting there. Our plate voltage is not sitting there at a single voltage. It's swinging between two values. And without getting into too much detail, the way we have to calculate AC plate voltage is, instead of just picking a voltage such as 20 volts, picking off the current and running Ohm's law, what we have to do is do it by changes. So we have to take a change in voltage right here between two values. Remember, we're swinging. We have this AC, we have this voltage. I'm going to draw it sideways. That's swinging like that. So we take a change in voltage and then find out its corresponding change in current. And so for our AC resistance, and change is indicated a lot of times in engineering by delta, like that, delta. So delta V over delta I. And that's indicated right here using more of a calculus notation. Same thing. So we find out these changes that we're swinging. Real simple. You can pluck them off the chart. So, for example, if a change in 16, I don't know, if a change in 10 volts equals a change in 20 milliamps, let's say, that would be a change in 10 volts equals a change in 0.02. That would give us our plate resistance. And I think they've done that for us here. So let me erase that, and I should have looked at this a little closer. Let me erase my stuff here. Let's see what they got. Okay, so here they said we have a change in voltage of 3.2, and we have a change in current of 10 milliamperes. So let me run that number. I'm going to take my calculator and take 3.2 and divide it by 0.01, and I get 320. And there it is. Plate resistance at that point in the middle is 320 ohms. And they've done it for a couple different values. Up here higher, at a higher voltage, 278. At a lower voltage, 527. Two things to note. Excuse me. Two things to note. One characteristic is similar to the DC curves. As you increase the voltage, the plate voltage, the resistance increases. However, look at these absolute numbers here. 278, 320, and 527 versus the DC numbers, 422, 500, and 800. AC resistance or impedance, let's call it resistance, is lower than DC. That's just something to keep in mind. That's all I want to say about this right now. It's important to keep in mind. Okay. One final thing before we move on to, we're going to get into some transformers. And this is just more of a nomenclature, something to keep in mind if you're really interested in tubes. There's something called static tube characteristics and something called dynamic tube characteristics. And don't zone out on me yet. If you don't even care about these terms, don't worry about it, but they are important. The differences between these terms. And it's super simple. Tube characteristics sometimes are given in a static condition. And all that means is these tube characteristics are measured without a load. And that's depicted here. Here's our diode. And here is our voltage source where we get to increase the plate voltage and measure the plate current. But look in the circuit. There's nothing else limiting the current flow except for the diode itself. There's no load. And these characteristics are unrealistic in the real world, but they do tell us something about the tube itself. And that's called static. Dynamic means we actually have a load in here, some kind of realistic load. And in real life, these tubes are always loaded down with something. There's always something that's going to limit the current flow. So this is the same situation here, even though there are different schematic diagrams. Same situation. We have a variable voltage source where we're going to increase our plate voltage. Here's our ammeter. There's our ammeter there. We get to measure current, cause and effect, except now we're putting an actual resistor or some kind of load in series. More akin to the real world. Something that's also going to limit the flow of current. So before, the only thing limiting the flow of current in here, right here, this is static. The only thing limiting the flow of current is the tube itself, its own internal plate resistance. In this situation, the flow of current will be not only limited by the internal plate resistance of the tube, but it'll also be limited by the parallel resistance of the load, in series resistance of the load in the circuit. That's going to serve to actually further reduce the plate current. And without getting into any more details, this dashed line is what we were just looking at, right here, static, no load. As soon as you start introducing this load here, like more in tune to what you'd find in the real world, then this characteristic line will change. And it's going to become lower because remember, for any given voltage here, let me just pick 20 volts in the static curve, we get a super high current. Once we add an inline resistance or load, for that same voltage, the current is going to be lower because we have extra resistance resisting the flow. And same here, this was an inline load of 1,000 ohms. Here's an inline load of 10,000 ohms. So again, 20 volts, our current is even going to be lower. So that's one thing that's going to happen. And the other thing that's going to happen, these lines are going to start straightening out and become more linear to some degree. That's all I want to say about that. We'll get into more of that when it's applicable. All right, I want to take a break, grab a cup of coffee, and pick up on, let's see what we have here. Oh yeah, look at that. I own this. Transformers and the AC operation, the alternating current operation of a diode, and we're going to look at an actual, we did this kind of once before, we're going to look at an actual power supply. And there it is. We're going to look at this power supply and we're going to analyze it. We do a light analysis, but we're going to analyze it and figure out how this power supply converts. This must be Europe or something. Maybe not, but 230 volts AC into 425 volts DC. I can draw the line DC over time. That's the time axis. So 425 volts DC, and there's time. There's AC. How do we do that? All right, take a break, come right back. All right. I took a break, but to you it was nothing. Okay, AC is applied to a diode. We've been mostly talking about direct current. Now we're going to talk about AC, which is what a diode does, in particularly related to our vacuum tube amplifiers. We need them in our power supplies. This is a vacuum tube amplifier circuit I pulled from the web, and it's divided into two pieces. Up here we actually have the audio amplifier. Put our audio signal into there. Got a couple driver stages here. Looks like we have an output stage here. And here's our output transformer and our loudspeaker. Down here is our power supply. And our power supply this is where our plug comes in from the wall. And here's where we convert AC to DC. Now this is a depiction of solid state diodes right here. But in a lot of people, it's interesting in the vacuum tube world, it is common to use solid state rectifier diodes in the power supply side of a vacuum tube amplifier. But a lot of people prefer vacuum tube rectifiers. You get different opinions on that. Different opinions. And I won't get into the merits of either one. That's up to you to decide. But let me show you what, and this is a bridge rectifier, solid state device. Don't even worry about it. I'm just giving you a dichotomy here. But if you were one who preferred a vacuum tube amplifier with a vacuum tube rectifier, rectifiers convert AC to DC, then that circuit would look something like this. Instead of that bridge rectifier, here's our rectifier using vacuum tube diodes. We're going to return to this and analyze this. I'm just starting out with sort of a summary because we're AC applied to a diode. Now, let's start out with transformers, and we're going to take a little bit of a diversion and just talk about what transformers do. And I think you might find this interesting if you don't already know. Now, this is my vacuum tube headphone amplifier. It doesn't matter whether it's a headphone amplifier or a speaker amplifier, but this is my vacuum tube headphone amplifier, and Macintosh is famous for putting stickers on top of their transformers labeling what they do. Not a lot of companies do that. And you can see we have an output transformer, and a power transformer. And that's typical of what vacuum tube amplifiers have. I just pulled this one off the web. This right here in the middle, the big guy, is often the power transformer. And this is an output transformer for one channel. And this is an output transformer for another channel, left and right. And there are big differences in terms of what a power transformer does versus what an output transformer does. No, they're both transformers. They both convert. They have turns ratios. They have turns inside them of wires, and they will raise or lower, step up or step down voltages. And let me just leave it at that, not to get too complicated now. That's what they do. But there's a big difference in terms of their function in the circuit here. The power transformer right here is in the power supply. And its function is to take incoming AC, and if you're in America, let's call it 120 volts RMS from the power company, and to convert it, step that voltage up or down. In solid state devices, we might step that voltage down. In tube devices, we might step that voltage up, to something like 500 volts. So it's either a step up or a step down transformer, and that's its function. The power transformer. Okay, that's the power transformer. The output transformers serve a fundamentally different function. And I'm not going to get into that right now. They do indeed step down voltages or up voltages. Okay, here's the output transformer. And they do indeed typically will take a very high voltage. Okay, a vacuum tube is let me just, I don't know if I can, let's see here, laser, I can't do that. A vacuum tube right here is I'm going to draw an arrow for high, is a high voltage, I stands for current, and low current device. And what this output transformer is going to do, these voltages here are way too high for a loudspeaker. We're still in the hundreds of volts here. So what this transformer is going to do is, through a turns ratio, it's going to step this voltage here down and take this low current and increase it proportionally. The power remains the same. So to drive our speaker, we need a lower voltage, but we need a higher current. And through that process, we do something called impedance matching. Now, I'm not going to get into that now. But the point being is the output transformer's function, while similar, is fundamentally different than the power transformer. And let's leave it at that now. We'll get into more of that later. Let's talk about, and I drew, this is a step-up transformer. Because remember I said that, for example, typically in tube amps, we need to step the incoming voltage up, because these tubes need hundreds and hundreds of volts to operate, more so than the power company gives us. There's also another function called isolation that I won't get into here. This power transformer also provides us isolation from the power company. There's no direct connection. There's no direct copper connection here. The only connection is made via a magnetic field. So it gives us a form of isolation as well. Forgot to mention that. All right. So we have a transformer. Sometimes you'll see these little bars right here that indicates an iron core. And these little squigglies are meant to represent a turns ratio. And all that means is when you have a transformer, I'm going to draw this iron core. Pretend that this is just a rectangle of iron. We're hollow in the middle, and where there's air on the outside. And this is just iron in here. Some kind of ferric material. And to create a transformer, we just take some wires and we wind them on what we call the primary side. That's the input side. Like that. We wind them around the iron. That's called the primary side. Then we have the secondary side over here. This is the output side that we're going to pull from. And we do the same thing over here. And if we're going to step the voltage up, we need a lot more windings over here. A whole lot more to step the voltage up. All right? If we were stepping the voltage down, we need fewer windings over here than over here. But we're gonna focus on a step-up transformer. So right here, E stands. We sometimes use V for voltage or E for voltage. E stands for electromotive force. So E or V for voltage. P stands for primary. S stands for secondary. So there's this ratio here. So the voltage that's on the primary divided by the voltage on the secondary is equal to the number of turns. Each one of these, one turn here is one turn. There's 2 turns, 3 turns, 4 turns. Is equal to the turns of wire on the primary divided by the turns of wire on the secondary. And you can see here there are more turns on the secondary than there are on the primary. So this is going to be a step-up transformer. It's going to result in a higher voltage on the secondary. So let's run some numbers here. So we start out, I didn't know how to approach this, but I like to look at things in terms of the turns ratio. There's a ratio of the number of turns of the primary to the number of turns of the secondary. And it can be done knowing the number of turns, or you don't have to know physically how many turns are in here. You can just need to know how much or how little it steps down. So let's say if I were to put 120 volts into this transformer from the wall, AC, and I know that I measure the output, and we're doing RMS voltage here, and I know I'm going to get 500 volts out, that's directly proportional to the number of turns. So 120 divided by 500 is 0.24. That's the turns ratio. Now, I can say this, that if the turns ratio is below 1, it's stepping the voltage up. If the turns ratio is above 1, we're stepping the voltage down. Don't get freaked out by that. No big deal. Let's just run some practical numbers here. Let's say we start out with 100 turns. And I'm not going to get too much more into detail. I just think this is really good to know. Let's say we start at 100 turns. Well, you can do this. You can make a transformer yourself. I've done it many times, especially growing up. For the most part, you buy them when you're building an amp because it's really hard to make this iron core yourself. All right, let's say we start out with 100 turns on the primary right here. And I know that I want to input 120 volts, and I know that based on my design, I want to output 500 volts. So how many turns do I need on the secondary? Well, first thing I do is I calculate the turns ratio. 120 divided by 500 is 0.24. Well, that's going to be the same ratio as turns primary to turns secondary. So all we have to do is take our 100 turns and divide it by 0.24. Okay, right here. Turns primary is 100. Divided by the turns ratio, 0.24, and we get 417 turns. And that's going to effectively create our transformer that's going to step up 120 volts to 500 volts. And to prove it, we'll state it differently. If we had 120 volts on the input and we divided it by our turns ratio, 0.24, we'd get 500 volts output. All right? And I've kind of, when transformers are depicted in a schematic, not always, but if it's a step-up transformer, there are going to be more windings in the secondary. If it's a step-down transformer, there'll be fewer windings in the secondary. And you can see that's kind of properly depicted here, but not properly depicted there. All right. Now let's move on from there. It's just good knowledge. It's awesome to know. Okay. I've already covered this. That's the turns ratio. This is for impedance matching, and we're not going to get into this today. This will come into play when we get into the actual design of the output stage of our amp. But this is a good resource right here. All right, let's get into what happens when we put alternating current or alternating voltage, but we call it AC, alternating current into our diode. Now here's our diode, here's our cathode right here, and there's our plate right there. And this is a depiction of alternating current. 0, positive, negative. And this is time. As time goes on, this is 60 cycles per second. So there are 60 of these. There's one cycle right here. That's one cycle. In America, we have 60 of these cycles, these alternating cycles in 1 second. That's 60 hertz. All right. So we are going to see what happens when we put AC. It's the same thing that happens when we put DC in, basically. So let's start out during our positive half cycle right here. And we're putting this voltage on the plate, by the way. So it's depicted right here, 0 to positive. That means the plate is going to start swinging from 0 to positive, and we know what happens when the plate goes positive. It attracts electrons and a current flows based on the internal resistance. This is why you need to know all this stuff we talked about. A certain amount of current is going to flow based on the plate resistance. And the load too. We kind of mentioned that. So current is going to flow, and our output is going to be this hump right here. It's going to flow in proportion, relatively speaking. There might be some distortion there, but relatively speaking, we're going to get an output hump. Okay. So this was our plate voltage, and this is what our output current is going to look like. All right. Output current is going to follow the plate voltage. Now let's look at our negative half cycle of voltage on the plate. And that's depicted here as this little hump that goes down below 0. Below 0. Well, we know that when the plate is negative with respect to the cathode, here's the cathode, here's the plate. When the plate is negative, it repels the electrons back, and no current flows. So that's depicted in this dashed line. Nothing is flowing right there. So we got to wait for this cycle to complete. No current flows. Right here, no current flows. Then we start back at 0. Then we start back at the next half cycle right here. And this repeats itself. So we get a series of humps that look like that. And this is called a half wave rectifier. Half wave rectifier. We're going to look at a full wave rectifier in a minute, where the series of humps will be like that. All right, so that's AC applied to our diode. And this is the very last slide, and this one's going to be fun, I think. Ooh, get out of here. Okay. I was trying to get my eraser. All right. Let me just start from scratch right here. So this, what you're looking at here is a... Oh, am I still recording? I better be. This is a power supply circuit. It's a pretty practical circuit for an actual amplifier. And so whoever the designer was said that, okay, I got typically we would have 120 in. I don't know why they're using 230 here. That's a lot of, I don't know if that's Europe or I'm not sure what, but let's work with it. We know as a designer that our wall supply is going to be 230 volts. And I know out here to drive my tubes, I want something akin to 425 volts DC. So if you were to plot it on time, there's this non-varying voltage that's going to be 425. And this input voltage is AC if we were to plot it over time. So the key here is not the absolute numbers. I'm not concerned with that right now. Is how do we get from this to that, and the process is called rectification. It's actually called rectification. I'm going to draw rectification right here. Plus filtration. Filtration right here. So to get from here to here, we need rectification plus filtration. Both. That's the key. I'll get into a little bit about the filtration, but we don't need to concern ourselves with that today. The key is rectification. So we kind of went through this before, but let's go through it again. So this designer has chosen a power transformer right here. And you can see it's properly indicated as a step-up transformer. There are more windings right here. And this says 2 times 500 right here. So what that means is, given 230 volts RMS, between here and the center tap. Now this transformer has a center tap. That means if I go back to my little depiction here, that means somewhere in the center of these windings we've pulled a wire off. Like that. That's it. It's a center tap. Now, so what that really means is if I was to measure voltage from here down to here, we would measure 1,000 volts. 1,000 volts. 2 times 500. So the turns ratio of this transformer, not that we even need to know it now, it's just out of curiosity, would be 230 on the primary divided by 1,000 on the secondary. The overall turns ratio, it's 0.23. So it's lower than 1, so it's a step-up transformer. All right, we don't even need to concern ourselves with that anymore because this designer's already chosen this transformer. All right, let's get into rectification. I always lose my cursor. It's a little tiny dot. Wish I knew how to make it bigger. Okay. Okay, now, so the best way to analyze this is analyzing the half cycles, the positive half cycle, then the negative half cycle. So let's start out with the positive half cycle. And if you want to know what that is, and I won't get into detail, if that's 230 volts, and I want to know what the peak voltage is, because that's RMS, I divide it by 0.707, 325 volts. So the peak voltage right here is 325 volts. And the peak negative voltage is negative 325. Don't worry about that. That's just the peak. So when we ascend to the very top right here, our positive half cycle, when we get to that point right here, what we're going to have is a positive, and I'm going to draw a negative sign. This is relatively speaking, and a positive and a negative. Now why? And this is going to be 325. Okay. This is a center tap, and this center tap comes down and it forms our ground. So everything is referenced to that. You're either above ground. Okay, let me draw ground here. If you're above ground, you're positive relative to ground. If you're below ground in voltage, you're negative relative to ground. So we've established our ground as the center tap. So when we're at this peak point right here, we have a positive relative to the center tap of 3. Ooh, I did that wrong. I did that so wrong. You know what? I'm not even going to cut this. Here's what I should have done. This is extemporaneous speaking for you. 500 volts divided by 0.707. It's 707 volts right here. .707 volts peak. All right. Yeah. Because we've stepped. I used 230 before, but we stepped it up to 500 RMS, which will be. Let me see something. What are these guys doing? Hang on a second. 230 times 0.707. 160. They must be using RMS. Okay, let's stick with this. These numbers aren't really adding up the way they should, but I'm just going to do it. All right, so 707. Okay, this is our ground here. Remember, this is our ground. So right here we have positive 707 volts peak on this line relative to ground. Now let's look what happens. This plate is positive. We're going to use conventional flow. It will conduct current. Okay, all the way to ground through these paths, and actually also through that resistor. Okay, these things are in parallel, and these these inductors are in series. Don't worry about what they do and what they are right now. The point is current flow. Now let's look at what's happening at the exact same time to the other diode right here. And this, as an aside, this is an indirectly heated diode. You can see the filament is depicted right here on its own little circuit that's tapped off the same transformer. We don't even need to care about this. It's irrelevant. It's fixed. That's the filament. Okay, let's look at what's happening down here. Okay, down here we have a negative 700, and at the same time, even though we're dealing with the positive half cycle, because of this center tap, this plate here experiences a negative 707 volts relative to the cathode. It will not conduct. Nothing is happening. So what we're going to get out here is our little hump. Current's going to flow. This is voltage, and I'm going to draw this as current. Current is going to follow the voltage out here as this little hump until this point in time right here that we reach 0. Now let's go to the negative half cycle. Let me start over again. Let's go to the negative half cycle. Now we're going to have 707, 707, except this time it's going to be negative, positive, negative, positive. Okay, so up here, this is our negative half cycle. We reach this point here, we're at negative, right up here, we're at negative 707 volts. So let's look at what's going to happen on the upper plate. Extremely negative, no current's going to flow like it did before. But down here, our plate is now positive 707, and current is going to flow in the same direction. So we're going to get another hump right there. Current flows in the same direction. So we've converted this negative half cycle into a positive flow of current. Okay, the positive half cycle, we convert it to a positive flow of current. The negative half cycle, we converted it to a positive flow of current. And as you know, AC just continues at 60 cycles per second, and we're going to continue getting these little humps like that. And this is direct current DC, because here is 0 voltage or ground, and this current will never go, this voltage here and will never go below ground. Therefore the current will only flow in one direction, that way, into the circuit. That's it. Now what these filters do right here is this series. How much do I want to get into this? Probably not much. I should draw current flowing that way, but this right here is very small. These are chokes or inductors, and these are capacitors. And let me put this in very simple terms. A choke or an inductor in series right here, with an alternating current. In this case, the current is, we don't call it AC, we call it DC, but it's pulsed up and down, up and down. So there is some high frequency content in here. And what this does is an inline inductor or a series inductor acts as a low pass filter. And it's only going to pass the low frequencies. It also acts as a storage device that stores energy and releases energy. So this will be a low pass filter, and so what's going to happen, it's going to tend to smooth these humps a little bit, like that. So when we pass this inductor, we're going to get this sort of, it's called ripple. It's called ripple. We're going to get a smoothing effect right there. This capacitor also, when a capacitor is in parallel like this, it affects, it's the same thing. It's also a low pass filter. And it will continue removing some of this ripple like that. Add another inductor, you'll get more of a reduction in ripple. Add another capacitor, eventually you'll get almost a straight line of DC. Just like that. That's all I want to get into for the filtration, but you can see the purpose is, first we rectify, we get DC, but it's kind of lumpy and humpy, and then we filter to smooth it out. All right, there you go. This is the end of part 3. I don't know what to say about this peak voltage of 707. I'd have to actually run the numbers, because you might think right here, I'm just thinking out loud now, that you're going to get a DC voltage of 707. Well, that's never the case, because these inductors are going to drop some voltage on them. They're going to reduce the voltage right here a little bit. So it's going to lower that 707. So what you're going to affect, let me just kind of draw this for you, and I'm just thinking out loud here. So here's our rectified voltage. When you start filtering like this, you're never going to achieve the peak voltage. You're going to achieve something a little lower. So by the time you're done filtering and smooth things out, the straight flat line DC you're going to get is going to be somewhere lower than the peak. Now I don't know that we're going to get from 707 down to 425 right here. I don't quite understand that. I'd actually have to go back and run some numbers here. I'm not sure how that works. It seems like that 425 in this scenario would be a little bit higher. But that's here and there. I'm just thinking of this from a design standpoint. Maybe that's true, but maybe someone's tested this and it works, but it just seems like that 425 would be a little bit higher. However, there's another thing that affects this 425 right here, and that's the load. Okay, the whole amplifier right here, the entire amplifier is going to be hooked up to right there. And that entire amplifier is going to draw a certain amount of, well, we got the 425 volts, but it's also going to draw a certain amount of current. And that current that it draws is further going to reduce this DC under a loading effect. And I'm not sure if that 425 is the loaded voltage or not. It's hard to tell. It just seems a little high, given an open, this is an open circuit, given an open circuit. But what do I know? I haven't designed a tube amp in decades. Okay. Stereopolice, I hope that was helpful. Ciao. See you next time.